So how do we derive our integrated rate constant if we don't have a first order reaction, but instead we have a bimolecular reaction or a second order reaction, such as this shown on the left? Now this is a special case of a bimolecular reaction where both of the reactants are exactly the same. So two molecules of A reacts to form the product C, and then from the arrow we can see that this is an irreversible reaction with only one rate constant. That's the forward rate constant, little k. Okay, so the way we start this up is that we're going to set up the rate equation so that we're looking at the consumption of A. So that means the change in A, the concentration of A at any given time t versus time is going to be equal to the negative of the k times the molecularity of A at A times T, and this is squared. And that's because two molecules of A are required to react with each other. So the molecularity, if this is the only step for this reaction, is going to be to the power of 2. And then the negative sign is because we're consuming A. If we were producing A, or for instance, if we were setting up the equation so that we were looking at the formation of C instead, this would be positive because we're forming that. Okay, so you can see that on the left side and the right hand side that there's terms of A at time t in both sides. So we can set this up so that all the terms are on the left hand side for A of t, and then we put dt on the right hand side. So we do that by multiplying by dt on both sides, and we divide by A of t squared on both sides. And that's going to give us an equation that looks like this. Equals negative k times dt. So that cancels out there. This cancels out here. All right. So now we have this, and what we're going to do is we're going to integrate on both sides to give us this equation where, because this is a to the t squared, what we find is that we have negative 1 over a to the t from a naught to at equals negative kt plus c. Okay, and I'm not going to go too much into this, but if you set this up and solve for c, what your final equation is going to look like is 1 over a t minus 1 over the initial concentration of A is going to be equal to kt. And then from here, you can solve for any concentration of A at any given time, as long as you know the initial concentration of A at the beginning of a reaction or at time equals 0, and then the time point that you're at and the rate constant.